Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about classification trees, which are a very useful model for classification, which is able to exploit nonlinear patterns in the data. Let's get to it. We're going to talk about classification trees and we're going to be focused on the classification problem. We will use the same running example as in the video on softmax regression, where we're trying to classify wheat seeds into three varieties. So the seeds can belong to the Canadian variety, the Kama variety, or the Rosa variety. And the features that we're going to use to perform this classification are two. They're the asymmetry coefficient of the seed, which I imagine quantifies how asymmetric the seed is, and the area of the seed. Both features are standardized. They were centered according to the sample mean over the whole data set and normalized by dividing by the standard deviation over the whole data set. So you can see here, just very briefly, that the Canadian seeds have higher asymmetry. The Rosa seeds have larger area, and the Kama seeds have both smaller asymmetry and smaller area at the same time. Okay, so we're hoping to be able to classify automatically new seeds based on these two features. The classification problem, in terms of notation, we give it the following notation: x1, x2, xn are going to be n feature vectors in our training set, and y1, y2, y2, yn are the corresponding responses, which are the labels corresponding to the predefined classes in our classification problem. So the xi's are d-dimensional vectors if we have d features, and the yi's indicate the class. In the wheat example, the class would be Canadian, Kama, or Rosa. So the yi's are going to have only three possible values. Our goal is to assign a class to new data. Vector x comes in with d features, and we want to decide what should be the corresponding value of the response. We apply probabilistic modeling to this problem, and we model the features as a random vector x. This is why x here has a squiggly line, because now it has random variables in terms of fixed deterministic quantities in each of its entries. And the label is also modeled as a random variable y, which is now uncertain. For a new data vector x, a reasonable way to perform classification is just to maximize the probability of the label given the observed feature. And when I say maximize, it's basically choosing the class that has the highest conditional probability given the observed features. If we do this, we're minimizing the probability of committing an error, so it's optimal in that sense. So it would seem that classification is easy, right? For each possible value of the feature vector x, I can just compute the conditional empirical probability of each of the classes within the training set, and then when I encounter a new value of x, I'll just look at those probabilities and choose the class that is more likely. This sounds great, except that it's generally impossible, because due to the curse of dimensionality, unless we have a very, very small number of features, it's going to be impossible to learn all of these conditional probabilities, because there's just too many possible configurations of the feature vector. So when we encounter a new feature vector, it's usually going to be unique in the sense that it won't be exactly the same to any of the feature vectors in our training set. So because of that, we have to make some assumptions when we're modeling. And when we perform a discriminative classification, what we do is we try to approximate this probability of the response given the features under some assumptions. We have already discussed this in the videos on logistic regression and softmax regression. There, the assumption we made was that we're going to use a linear model that was then going to be mapped to probabilities either by the logistic function or by the softmax function. Okay, so the assumption we made was that you can, like the estimator, the classifier, is going to just perform a linear operation on the features and then map that with a fixed function, a fixed link function to probability values. How does this look for our example? This is what the features look like for the different examples. For the Canadian variety, this is the learned linear function that is applied. I feel that I'm saying function a lot. These are the logits. If you've seen the video on logistic regression and on softmax regression, when we perform this linear combination of the features, we call that logits, which are then fed into a logistic function or to a softmax function to get the probability estimates. They're of course linear in terms of the features, and then they get mapped to probabilities. So now our goal is going to be to try to model nonlinear relationships between the features and the response, which cannot be captured with a linear model such as logistic regression or softmax regression. How are we going to do that? We're going to build a classification tree in the spirit of regression trees. So in the video on regression trees, we explained how regression trees are able to capture nonlinear dependence that you cannot capture with a linear regression model. Now we're going to do the same, but for classification. The idea is to build a binary tree that partitions the feature space into these joint regions. We're going to visualize exactly what I mean in a moment. And then we're going to assign constant probabilities to each class within each of these regions. Okay, so let's take a look at how that looks for our wheat varieties. This is a tree that was learned directly from the data that I showed you before. Remember that there are two features, the area, which we're going to denote by A, and the asymmetric coefficients, which we're going to denote by C. So our tree is going to partition the whole feature space according to whether A is smaller to 0.18 or larger than 0.18. Then this region for which A is smaller than 18 is going to be further divided into two regions according to this threshold and the same features. We're again going to divide the feature space according to the A feature. Then we're going to divide the other one also according to the A feature. And then we're going to use the C feature to further divide some of those regions. Let me show you what this actually looks like. Now I'm going to attempt to draw these regions, and this is a relatively large tree, so now I'm going to pay for being lazy and not doing this offline before, but let's see how it goes. This is going to be approximate, okay? So bear with me if I make some mistakes. So first we're going to cut the partition. You're going to partition the feature space according to the A feature. So the threshold is 0.18, which is approximately here, I would say. Boom, okay? So now we have two regions, this one and this one. Now we have we're going to separate the left region according to whether the feature A is below or above minus 0.5, and we're going to separate the right region according to whether the feature A is below or above 0.78, sorry, which is roughly here, and for the left split, it's more or less here, okay? And then finally, we're going to use the left, what am I saying? Oh, that's nice. We're going to use, I should have used that before. We're going to use the other feature, okay, which is the asymmetric coefficient, and we're going to threshold according to whether it's larger or smaller than 0.31, but this is only for the region where A is smaller than minus 0.5. So roughly around here, that's where we're going to cut up that particular region. And finally, here we have a threshold where the coefficient is smaller or greater to minus 0.83, but this is only active in the region where A is between 0.18 and 0.78, so roughly here, and the threshold is around here, okay? So now you will see that for each of the leaves in the tree, I'm running out of colors, so this is not going to be, like the colors are not going to be super consistent. Hopefully you can forgive me for that. But basically now for each of the leaves in the tree, we have different regions. We have partitioned the feature space into regions corresponding to each of the leaves of the tree. Here A is between minus 0.5 and 0.18. Let's see, I'm gonna run out of colors maybe. Here C is below minus 0.83. Here it's above minus 0.83. And finally, do I have another color? I have another color, this last region. So our binary tree cuts up the feature space into disjoint regions that cover all of it. And now we're going to assign probabilities within each region. And then later on, I'm going to tell you how you learn the tree from data. So there's two key questions that I just kind of said. How to compute the constant probabilities within each region and how to build the tree. Okay, so now let's first concentrate on the question of how to assign constant probability estimates within each region. So now I'm going to assume that we're only considering the feature response pairs. Here, more than response, it should be label, but that's okay. In region R, okay? So yi contains the label corresponding to each of the xi's, and we're only going to consider the nr data points that are within a certain region R. And we're going to choose a constant probability estimate theta that will only be assigned to that region. The way we're going to do it is we're going to maximize the conditional likelihood of the labels given the features. This is exactly the same as what we did with logistic regression and with softmax regression. So the idea is that the likelihood is the likelihood of the observed labels. And remember, we're only considering here, this should be NR actually, because we're only considering the labels within the R region, conditioned on the features observed again in the R region. And we're going to make two very reasonable assumptions. Or just to clarify notation, here we're modeling the ith feature as a random vector xi and the ith label as a random variable yi, and we want to maximize the conditional probability of the observed labels, which are these guys, given the observed features, which are these guys. This full conditional probability in general, we're not going to be able to maximize it, so we have to make some assumptions. The assumptions that we're going to make is analogous to the assumption that we made when we were fitting parametric models according to the likelihood, which was that everything was independent and identically distributed. Here, we're going to assume that everything is identically distributed in the sense that you have the same conditional probabilities of a label given the features for each of the examples. And the independence assumption is going to be that the labels are conditionally independent given the features, which means that we can factor this joint conditional probability into a product of the conditional probabilities of each of the labels given the features. And we're going to also assume that the labels are conditionally independent from the other features if you see their own feature. So if we see xi, then we don't care about the other feature vectors. So that simplifies to a product of the conditional probability of each of the observed labels given just the corresponding observed feature, which hopefully makes sense. And it's analogous to this IID assumption that we make when we fit parametric models. In our case, because we're only constrained to be within this region where we just want to produce a constant estimate, the conditional probability of each class is basically just the corresponding entry in this theta vector that is constant. So this theta vector is going to assign one probability to each of the three classes in our example. or C classes in general. So for the data points where the true label here is K, then the probability of seeing that label given the feature is going to be theta K. Because again, we're assuming that we're only considering the data set within the data that are within one region, and within that region, we assign a constant probability to each class. The question is, which is the best constant probability that enables us to optimize the likelihood of this observed data? Okay, so that's what we want to do. We want to maximize this likelihood. If we constrain ourselves to two classes, imagine 0 and 1, then this is exactly the same as a Bernoulli likelihood, because we're seeing zeros and ones, and we want to find a constant probability estimate that best fits that data from the point of view of the likelihood. And if you go to the video on maximum likelihood for discrete random variables, you will see that the maximum likelihood estimate is very reasonable. It's just the proportion of ones. Okay, here I said 0 and 1. Let's imagine it's 1 and 2. Okay, so the proportion of ones and the proportions of twos. So if you have, I don't know, 10 data points in your region and half of them are ones and half of them are twos, you're going to say that the estimate for the probability of a 1 is 1/2 and the estimate for the probability of a 2 is 1/2, which makes a lot of sense. By maximizing this likelihood in the same way as we did with the Bernoulli likelihood in the video on maximum likelihood for discrete random variables, you can show that for an arbitrary number of classes C, the best constant probability estimate in terms of likelihood is actually going to be also the empirical probability of each of the classes. So if 25% of the data points belong to class 1, the probability estimate for that class within that region is going to be 0.25, and so on and so forth. In our case, with these width varieties, these are the regions, these are the different probability estimates that we had for Canadian, and we're going to see where they come from. So in this region here, there's only Canadian data points, so the estimated probability is 1. In this region here, maybe I'll use another color. In this region here, there's slightly more than half Canadian points, slightly less than half gamma points, so the probability estimate is a bit more than 0.5. And finally, in this region here, there are no Canadian points, the estimated probability is 0. Again, don't worry too much right now about how we estimate these regions. We're going to talk about that in a moment. This is if you have already estimated those regions, what's the best constant probability estimate within each region, and that's going to be the proportion of data points within that region. That's the best way of fitting the data with this model, and hopefully that makes sense. So if we look at gamma, again, we have a region where there's just gamma points. So boom, there we have a 1. Here, as I had just mentioned, there's a bit less than half gamma points, so we have a bit less than 0.5. Then we have two regions where there's 0 gamma points, so the probability is 0, and so on and so forth. For rosa, here there's just rosa points, probability is 1. In between, there's some more rosa points than, I guess that was gamma, so the estimate is going to be around there. And here, no rosa points, the probability estimate is 0. Perfect. So we know how to assign the constant probabilities to each of the regions represented by the leaves of the tree. But how do we build the tree? That's the key question. And it's quite natural to build the tree by choosing the tree that has the maximum likelihood. That's a great idea, except that it's completely intractable to do this in general because there's too many possible trees. We discussed this a little bit more in detail in the video on regression trees. If you start counting the possible bifurcations that you have in a tree of a certain depth, and then you realize that for each of these splits, you're going to have to choose the feature that you will use to split and the threshold that you would use to split that feature, there's just too many possible trees to consider. So you cannot just consider them all. you have to have some strategy to build the tree in a tractable way, and the way that you can do it is by recursive binary splitting, which sounds complicated, but it's basically just growing the tree one bifurcation at a time and choosing the bifurcation that maximizes whatever cost function you care about. So if it's a cost function, you probably want to minimize it. But basically that optimizes the metric that you care about. In regression trees, we wanted to minimize the residual sum of squares. Now we want to maximize the likelihood. So what we do is we consider the log likelihood of the whole tree. Before, we were looking at the likelihood of only the data within one region. Now we're going to look at the data over all the regions, but the argument is exactly the same. We're still going to model the features as these random vectors xi and the labels as these random variables yi. And we're going to make these two assumptions where the labels are conditionally independent given the features, and each label is conditionally independent from all the other features given its own feature vector. So if we do that, then we get this likelihood where we have the conditional probability of each label given the observed feature vector, and according to this classification tree, the classification tree model, this conditional probability will depend on what region the feature corresponds to, right? So first we have to see xi, what region does this correspond to, and then we're going to just assign the constant probability estimate that corresponds to that region. So we have our M regions. The way this is going to work is we're going to look at all the possible classes, and we're going to look at all the possible all the possible data points. So the data points that correspond to this class. So first, you can write this in several ways, and I just managed to confuse myself, but let me say this right. First, we look at the first class, and then we look at all the data points that belong to that class. We check the feature vector, we see what region it belongs to, and then we pick the entry of the constant probability vector corresponding to the class that we were talking about, okay, the class that was observed. We do this for all the classes, and that covers all of the data points. That is going to be the log likelihood, the conditional likelihood of, not the log likelihood, the conditional likelihood of the data. Because these are all probabilities and we're multiplying a lot of probabilities, we're going to get a very, very small number. In order to get better numerical stability, we usually use the log likelihood of the data. That's what we actually maximize. Because we're taking the log, this just becomes sums, and here you can see the log there. All right, so now we want to choose the split that most increases this log likelihood at each step as we're growing the tree. If a region R is split into two regions, the difference between the log likelihood before the split and after the split is just the term here that corresponds to region R. So it's only going to affect the data points for which the feature vectors are within the region R. Those data points had this contribution to the log likelihood, the number of points times the logarithm of the corresponding probability estimate, because the probability estimate is constant within that region. After we perform the split, the probability estimate is no longer constant within that region. It's going to be constant within this subregion, and then also constant within that subregion. So when you look at the contribution of those two subregions to the whole log likelihood of the tree, it's going to look like that. Okay, I should have used a different color for B. There's this contribution from A that is in purple, and this contribution from B. And we want to choose the region, the feature, and the threshold such that after the split, we maximize the log likelihood as much as possible. There's a very interesting connection between this way of building a tree and the entropy of a PMF. Okay, so in case you have never heard of entropy, entropy is a measure for the information within a random variable, and this is This is how it looks like. If you have a PMF of a random variable with C entries, the cross entropy is equal to minus the sum of the logarithm of the probabilities weighted by the probabilities. So this looks perhaps a little bit complicated if you've never seen it. If you want to know much more about entropy, you should go read the book on information theory by Thomas Cover, which is really amazing. But if you don't, I'll just tell you that entropy essentially quantifies to what extent the random variable is usually equal to the same values, and to what extent it's like super uncertain and you really can't be sure to what value it's going to equal. So to make that very precise, let's consider a Bernoulli random variable that has two possible values, okay? And here we see the probability that it is equal to the value 1, okay? The entropy of the random variable, so realize that, for example, when the value 1 has probability 0, value 2 has probability 1. The entropy in that case is minimal, it's 0. Why? Because there's no uncertainty within the random variable, which in the framework of information theory, they connect uncertainty and information, because when the random variable is revealed, you have learned a lot. But if you always know the random variable is equal to 1, if it's revealed, you learn nothing. That's why the entropy is low. The entropy is maximal when there's 0.5 probability of seeing a 1 and 0.5 probability of seeing a 2. And it's 0 again if we know that the first entry is always going to be, the first class is never going to appear, right? I got this completely backwards. Let me say that again. The entropy is 0 if, let me say it again, if we never see the first class, or if we always see the first class, and if we see the two classes with equal probability, that's when the entropy is maximal, because revealing the value of the random variable gives you the most information. So I hope I didn't confuse you too much. Basically, if the entropy is large, then the probability is distributed between the different possible values. If the entropy is low, that means that some values completely dominate. So the entropy quantifies the purity of the random variable of these probabilities. If we have very low entropy, this means that one class dominates. And that's exactly what we want in classification. We want regions where the probability is equal to 1 for one of the classes and to 0 for all the other classes, because that means that within that region, there's just data points corresponding to one of the classes, which is amazing. We're going to get perfect classification. So that's why we try to minimize entropy when we're building our classification trees. Alternatively, you can use other metrics that quantify purity, and a very popular alternative is the Gini index, which is something that you can actually use in scikit-learn if you are fitting a classification tree. And in fact, I think maybe the Gini index might be the option by default, but you can also use the likelihood, and typically the estimates are very similar. So when we want to split a region R into A and B, we want to maximize this change in the log likelihood. We want to make the new log likelihood as large as possible with respect to the old one. And this can be framed in terms of entropy, because here, like the entropy of a certain vector of probabilities is equal to the logarithm of each entry times the probability itself, and then you sum over all the values, and then you put a minus here. If you realize here, theta A, for example, of k is just equal to the number of points in region A that are assigned to class K divided by the total number of points in that region A. So if we divide this by NA, this by MB, and this by NR, we get the entropy at region R multiplied by the number of points in region R. Okay, realize that there's a minus here, minus the entropies in regions A and region B multiplied by the number of points. So basically, if we maximize this, we're trying to find the split that pushes the entropy down as much as possible. Okay, makes sense? So now let's take a look at an example. So in this example, we have 3 data points, which are class plus, and 2 data points, which are class minus. And there's just one feature, okay? The feature is represented in the horizontal axis. So this plus is 0.5, this one is 3.5, 4.5, 5.5, this minus is 1.5, and this other minus is 2.5. And now we want to split, like the region. This is the region in the feature space, okay? Maybe I'll use another color. This is the region in the feature space, and we want to cut it, right? We want to split it to create 2 new regions, and we want to split it in a way that minimizes the change in the entropy of the new 2 regions with respect to the previous region, or alternatively maximizes the negative entropy, which is the log likelihood. Okay, we're maximizing likelihood, minimizing entropy. Here we're only choosing with respect to one feature. In general, when you're fitting a classification tree, you would have to consider all of the features, splitting according all of the features, and you would have to consider how to split each of the regions. But here I just want to show you that if you use this criterion of maximizing the likelihood or minimizing the entropy, you're going to obtain a reasonable split. Okay, so let's start. So this is a possible split, right? We could say, okay, let's just split here so that these guys belong to one region and this guy belongs to this other region. So here on the left, the probability of a plus is 1. And on the right, the probability of a plus is 3 divided by 5, which is 0.6. Okay? That corresponds to a negative a combined entropy, because we're weighting the entropy by the number of points in each region, equal to this. Okay, this is the log likelihood. This is the change in log likelihood that we would observe. Well, actually, no, I was going to say this is a change in log likelihood that we would observe if we split the region, but that's not true because I have not included the term that captures the log likelihood of the whole region, because that's going to be the same for any of the splits. So I just wanted to make things clearer here. So this is the criterion that we would use to split if we wanted to maximize the log likelihood. Because again, we can ignore the additional term that would be something plus nr h theta r, because it's going to be equal for it's going to be the same for any of the splits. Okay, so what if we split according according to 2 instead? If we do that, then we get one region where the probability of plus is 1/2, and another region where the probability of plus is 3/4. The corresponding weighted entropies, negative entropies, are equal to that. So this is a better split. Now, when I saw this at first, I was a little bit confused, because here it seems that this is quite a lot more extreme than this, and these two are not that different. So why is our criterion so much better in this case? I would recommend that you stop the video and try to think about it before I tell you the solution, because this will show that you're understanding what I'm talking about. Okay, the key here is that each of these entropies is weighted by the number of points. So it's great that this guy is so extreme, which is going to bring its entropy down to essentially 0, but it's only weighted by 1, whereas this other guy is weighted by 5. So it dominates and it brings down our metric. It's not a good split because of that, because there's just 1 point on one side and 5 points on the other, even if one of the regions is very pure. All right, so what happens if we split here down the middle? On the left, we have the probability of a plus is 1/3, and on the right, the probability of a plus is equal to 1. And for now, that's the best split. It's a split that is going to decrease the entropy as much as possible. And in fact, it gives us a region that is pure and has quite a few points, 3, and a region that is not pure, but where at least the minus label dominates. And in fact, that's going to be the best solution. If we look at the two other possible splits, I'm going to let you work out the probabilities. They're not as good. So this shows that when we maximize this metric, we obtain a split which is actually very discriminative, because we're trying to build regions that have as many points as possible while being as pure as possible, which is exactly what we want to be able to perform classification with our classification tree. So this log likelihood metric makes a lot of sense. This log likelihood that we're trying to maximize while building the tree in this greedy way. So let's go back to the width varieties. We want to build a tree for these guys, and what we're going to do is recursive binary splitting. So we would do exactly what I did for the simple example, but now we'll have to consider every region, every possible feature, in this case there's only 2, the area or the asymmetric coefficient, and every possible threshold, and we're going to choose the splits that increase the log likelihood the most. Equivalently, they're going to minimize these weighted entropies so that we get regions that are as pure as possible. We do that. I'm not going to draw a picture about how we do that because that would be very complicated, but basically, first, this is the best split. If you're just going to make one split, this is the split that's going to give you the best log likelihood, splitting according to feature A and threshold 0.18. Then, between these two regions, the best thing we can do is to split that region according to the feature A, and now the threshold is minus 0.5. The next best split between these 3 regions is to split this one according to the feature A. After that, the best split is to split this region according to the feature C, and so on and so forth. So hopefully, like this, you can understand how this recursive binary splitting procedure works. Every time we generate new regions, the probability estimates within those regions are just a fraction of data points corresponding to each of the classes, as we showed before. The final estimated probabilities, we already saw them before, but let's take a look at them. Again, actually achieve pretty good classification because they manage to build regions where one of the classes dominates. Okay, these are the probability estimates corresponding to that tree that we just saw. It's important to highlight that this gives us an interpretable model, right? If the value of A is, let's do an example. Imagine that the value of A is equal to 1 and the value of C is equal to 0. So in that case, we would say, okay, A is greater than 0.18. Okay, maybe I'm gonna do something a little bit different so that it's a bit more interesting. 0.1. Okay, 0.1 is a more interesting one. Let me erase that. So A is equal to 0.1 and C is equal to 0. So now this is not true anymore. We're here, right? Because it's smaller than 0.18 and it's greater than 0.5, and again we don't use C. Amazing. So let me say that A is equal to minus 0.8 because I want to show you how to use the C feature. Okay, so now A is smaller than 0.18, smaller than 0.5, and C is smaller than 0.31. Boom, we're going to get that probability estimate. That probability estimate is equal to whatever it is because C is smaller than 0.31 and A is smaller than minus 0.5. So we have directly an interpretable reason of why we chose that probability estimate, and this can be very important when we're performing classification in certain real-world applications. Okay, so what have we learned? We have learned how to build nonlinear classification models using trees. And that's all I got. Thank you very much.